Okay, well, welcome to this afternoon's talk. This is the first of two talks on survival analysis um, and I'm going to talk today about univariate methods, some summary statistics, and I'll show you in a minute what the topics are going to be. And then in a month, Dr. Zhang will be here talking about regression models that one can use to study survival analysis outcomes. Does everybody have a handout, a copy of the handout? Okay. Okay, so I guess I need to make the usual disclosure here that I'm not getting anything out of this, but hopefully you're getting something out of it. What I'm going to talk about today are some of the basics of survival analysis. The first topic that I want to spend a little bit of time on is the difference between the two kinds of survival data that we see, or the two kinds of lifetime data that we see. What is usually called survival data, where we have a single event of interest and we're trying to draw some conclusions about it. And then the notion of what's called competing risk data, where we have multiple events or causes of death that are competing for the mortality of a person or a unit. And then for survival data, I'll try to give you a rough idea of what the two basic quantities are, namely what the hazard rate is, and this is what statisticians usually use to measure survival data. And I'll try to show you how it's a useful tool for interpreting aging and patterns of failure. And then the basic survival function. And I'll show you a little bit about the Kaplan-Meier estimator, which is the basic estimate of the survival function and what you can do with it. And then I'll show you how we go about estimating in the modern day competing risks in terms of what's called the cumulative incidence function. And then I'll show you a little bit about how we go about comparing two or more groups using what's called the weighted Logrank test. I won't write many formulas. I'll try not to write many formulas. I'll try more to give you a feel for why things work and show you through an example how to interpret some of these basic quantities. So survival data usually is data on the time to a single event. And it could be the time until death. It could be the time until treatment failure. A lot of the examples I'll give come from my working with the bone marrow transplant registry. So there, we're interested in death or relapse of a patient that was given a bone marrow transplant to treat leukemia. So survival time data would be the time until death or relapse, whichever comes first. It could be time to equipment failure. Could be time to a variety of different things. But there's one particular event that once it happens, the ball game is over and we don't see any more information on the patient. Now, survival data is of course complicated by the fact that not everybody dies. If everybody would die, then this would be a very simple discipline. I probably wouldn't be talking to you, but unfortunately, you'd probably be out of business as well. So we have patients who the last time we saw them, all we knew was that the event was yet to happen. So the last time we saw them, they were alive, and they're considered as censored observations. And we don't want to throw them away because they give us some partial information about how long the person was going to live. The longer they were until they were censored, that tells us something about the chance of them surviving a particular time. The kind of data that I'm talking about is usually called right-censored, in that all we know is that the survival time occurred to the right of when we last saw the patient. You may have other kinds of censoring, left censoring, where all you know is the event has already occurred. For example, if you were studying the age at which children, or age at which somebody started smoking, you may ask them how old you were when you started smoking, and some would say, well, I already smoked, but I don't remember when I started smoking. So all I would know is that that age was, in that case, left censored, in that it was prior to some point in time. So we're going to stick with right censored because that's the easiest to deal with. And of course, for the uncensored data, we see the death time. And for the censored, again, all we know is that it's beyond that point. And we're going to assume that the kind of censoring we have is what's called non-informative, which means that the times at which these people are being lost is not really telling us anything about the survival time itself. So people are just lost because they're lost. They moved out of town, not necessarily because they were healthy or because they were about ready to die. They just moved out of town and we lost track of them. And that's what we mean by independent censoring. Now, I'll be illustrating a lot of things on some hemopoietic stem cell transplant data, and just want to mention a little bit about what the data looks like up front. So it's a study of 866 AML or ALL patients. They all got a transplant. Be a long hour here. Okay. The main effect that we'll look a little bit at when we get into testing the difference between groups was the kind of preparative treatment that they had before they got their transplant, whether it was non-myeloablative, reduced intensity, or myeloablative. Myeloablative is sort of the standard, and these other two are considered less toxic. And the type of events that we would be looking at here with survival data would be, as I said before, death and treatment failure, which is relapse or death, whichever comes first. Now, the other kind of data that we may see is what's called competing risk data. And here we have two or more events that are competing for the failure or the death of the patient. And what we see is we see a failure time and a cause of failure for each one of the patients. And of course, once they fail from one cause, we assume that we don't see them anymore and there's no longer any more information coming to us from them. So examples in the transplant situation of competing risks, we could be interested in the death in remission, which is usually called the treatment failure, the disease-free survival rate, or the death in remission rate. Of course, once you die, and you die without relapse, it's impossible for you to relapse after death. And relapse would be a competing risk for death in remission. Once you relapse, you can no longer die not in relapse. Other classical examples of competing risks are dying from various causes. So somebody dies, they could die from heart disease, they could die from an accident, they could die from cancer, they could die from a variety of causes. In engineering applications, this is what happens when you have series systems that are put together. And you could have the system fail if any one of the components failed. And once one of them fails, the whole system has failed. So we're interested in summarizing the event probabilities for this kind of data as well. Just a little schematic here. We start out in some kind of a healthy state, and then we can go to any one of k different competing risks, and once we get into that state, we sort of stay there forever. We can't go to another one. The summary statistic that we usually use here is a little different than what we use for survival data. It's what's called the cumulative incidence function. And it's simply the chance that an individual has failed from a particular cause prior to some point in time. So the probability that you would fail from cause 1 prior to time t would be the cumulative incidence of cause 1. You'd have another cumulative incidence function for cause 2, and so on as you move through the different causes. And I'll look a little more at the properties of this in a couple minutes. So the sample data that we could have in the transplant setting, the competing risk data could be, as I said before, death and remission or relapse, whichever comes first. We could be looking at acute graft versus host disease and death without acute graft versus host disease as two competing risks. Once you get acute graft versus host disease, you can't die without ever having it. And obviously, if you're dead without having it, you can never get acute graft versus host disease. Example of 3 competing risks in the hematopoietic stem cell setting is looking at engraftment or return of the platelets or the neutrophils to sort of sustaining levels. A second event could be a second transplant, which basically means that you failed having your immune system be reconstituted, or death without engraftment. So we have sort of 3 competing risks here that we're interested in looking at. Now, going back to survival data, as I said, there are 2 basic summary statistics that we look at in this case. The first and simplest one to understand is simply the survival probability, or the survival function, sometimes called the survivorship function. This is usually denoted by S of x, and it's simply the probability that a person is alive at time x. So if we were looking at transplant data and the event was death, it's simply the probability the person hasn't died at 6 months, 10 months, 12 months, whatever. Very easy to understand, kind of maybe the thing we'd like to tell a patient. On the other hand, there's a second parameter that is what most of survival analysis is based on, particularly regression models, and that's what's called the hazard rate. And the hazard rate is simply the death rate. It tells us, and I have one of maybe 4 mathematical formulas here. If you don't get it, don't worry about it. It basically is the chance that you would die today given you were alive at the start of the day. So it's the rate over time of how quickly you are dying. It's the probability that somebody alive at a given point in time dies in the next instant of time. And it's a rate, okay? This rate tells us then something about aging. If we look at a graph of what the hazard rate is, it tells us sort of how quickly people are experiencing the event. And the pattern that we have, as we'll see in a minute, gives us a lot of information about what the mechanics are of the phenomena that we're looking at. So different patterns are telling us something about the aging mechanism. If you have a hazard rate that's constant, this is the classic example of a light bulb. A light bulb doesn't remember how old it is. Then you don't have any aging. And you would have a hazard rate that was just a number for any value of t. If you have a hazard rate that is increasing with age, then that suggests that the older you are, the more likely you are to die. And that's the usual kind of aging setup. You could have a decreasing hazard rate, and this is something that would show negative aging. And this may be what you get if you're looking at some kind of surgery, major surgery. You know, right after major surgery, you have the highest risk of death due to complications and due to infections. And having been in the hospital over the weekend, just being in the hospital and not getting any sleep. So your hazard rate may go down the farther you are away from that point. And looking at the hazard rate would give us an idea of what that failure pattern is. And then there are two other kinds, the bathtub kind and the hump-shaped kind. So here are sort of what the graphs look like. A hazard rate that would look flat like this. Again, remember, this is the chance that you would die tomorrow, given you were alive today, or you die in the next instant, given you're alive today. If that's constant, then you're not aging, and you expect to have a hazard rate that would be flat. Something that was increasing, like this one, would be aging. Now, the not so obvious ones, perhaps, are the bathtub-shaped rate that looks like this. Now, if you think about it, when a child is born, there's infant mortality, and as you have a relatively high risk of the child dying right after birth. Not super high risk, but there's a risk, and that risk gets smaller and smaller as you move away from the birthday to maybe a year or two. And then it's sort of flat through being a kid, maybe through puberty, until you get to somewhere maybe 17, 18 years old, and then you start aging. And the older you are, then the more likely it is you would die. So this bathtub-shaped rate is sort of what you would expect the natural history to look like for someone that, for natural history for any kind of animal. So, show you a little bit how to estimate this. And if you have estimates, then you can use this to speculate on different mechanisms for what failure may be. Now, there are other basic parameters that we may want to know about. And they, again, come from the mean. We'd like to look at, from the Kaplan-Meier estimator, the survival function. Sometimes you're interested in knowing what the average time to death is, or the mean time to death. And it turns out when you have positive quantities, like we have, for the time until death, if you look at the area underneath the survival curve, that gives you the mean, the same mean as you would have computed if you had taken an elementary statistics course. There's some calculus involved here and a little mathematical trick. So the area underneath the survival curve is what the mean turns out to be with survival data. And we'll use that to come up with an estimate. Now, I'll show you in a minute that there's a complication using the mean. So quite often what's reported is a median lifetime. And just to remind you, the median is the point where half the people are alive and half are dead. The time at which half are alive, half are dead. And you aim on a percentile rather than the median. And again, these are quantities that we can estimate fairly easily, and I'll show you that in a minute. Okay, now, you can take or leave the stuff in yellow here, and this is about most of what I have here for survival data. The basic estimate that we use for estimating the survival function is what's called the Kaplan-Meier estimator. It's a famous paper due to Kaplan-Meier in 1958, but really it goes back to the 1500s. It was one of the first statistical methods that were developed. It was developed and used a lot in the 1900s by this guy named Greenwood, who the variance is named after. So this is one of the earliest statistics that are around. And the Kaplan-Meier estimator is found, and if you don't care how it's found, it doesn't matter, because you can get the Kaplan-Meier estimator in almost any computer package that's available to you. What we do is we look at each point where somebody died, and we compute the number of deaths at that point and divide it by the total number who could have died. So this is an estimate of the probability of death at that point. And then we kind of multiply 1 minus these things together over all the death rates. This guy right here is an estimate of the hazard rate, and the hazard rate and the survival function are connected mathematically through this product business here. So it's an easy thing to compute. If you want to compute it, and I'd be happy to show you and write down a more specific formula for you. But it is, as I said, in almost any package that you could imagine will have it for you. And associated with it is a standard error, the same way there is with any statistic. And here the standard error is called Greenwood's formula, and it's given by this thing in yellow. I don't even really want to say much about it. Oop. So what do these things look like? Here is what the Kaplan-Meier estimator looks like, coming from the 3 different treatment arms that we had in the study. And well, we can see that it's a function that starts at 1, and it gets smaller and smaller the farther out you get. And theoretically, if you went all the way out as far as you could go, it would drop to 0, although it usually doesn't, because there's people that are lost before you got there. The curve itself only has a jump at places where there was a death. So quite often what people do is they put these little bars here on the curve. The little bars show you where the censored observations were, and the places where the curve jumps shows you where the events were. Okay? And here, well, we can kind of look at the 3 curves, and it certainly looks like the patients that were in the blue curve, which was, I believe, the non-myeloablative group, they did much worse than the other 2. Their chance of living was at, let's say, 40 weeks was about 0.3 something, maybe 0.2 something. These other guys are up around 0.4 something. Okay. So it gives us just a way of describing how likely it is a person is alive at a given point in time. Sure. Yeah. It's just a fluke.
Okay, so you don't look for why that might be?
Why they had less censoring?
Yeah.
Well, you may want to look at it. It doesn't, we kind of like to look, in practice we would look at each one of the 3 groups and do that before we looked at the curves. The fact that it's the bottom curve does not result of having fewer censoring, but
Visually different, but I thought I would ask the question.
yeah, although it's a little hard to tell, because can't really see the censored observations very well up in here. And I do think, if I remember, that these have roughly the same censoring rate, and they have the same follow-up rate. What we usually look at is we look at how much data we should have had if, well, okay. You have a study that starts at some point in time, it ends at some point in time. One reason people are censored is because the study ended. Okay? So if you look at between when you start and when you end, you can compute, if nobody in between was lost, what the total time should be, where those that died contribute how long they were there, and those that were not deaths should have contributed the whole interval. And compare that to what you actually got. And when we do things in the transplant registry here at the college, we expect that to be at least 90%. So that's really what we look at, is to see whether the follow-up, the amount of follow-up is the same in the different groups by using that index rather than the number that were censored. Okay. Any other questions? Pardon me?
There's a lot more patients in the group 4, so you're going to have a lot more censored data, right? Because there's like...
Right, right. It is a bigger group, so. Yeah, I mean, this isn't a perfect randomized clinical trial. This is an observational study, so. So the data is what the data is here. Okay. Now, usually just reporting the curve is sometimes misleading, because as you noted, the sample sizes were different in the different groups. They're going to have different size standard errors. So just because two curves are different in terms of the picture that we drew doesn't necessarily mean they're really different if one was based on 10 patients and one was based on 1,000. It could just be numbers that are doing it to us. So what we like to do is compute interval estimates that go along with the survival probabilities. And there's two kinds of these that we can compute. One is a pointwise confidence interval, and one is a confidence band. In a pointwise confidence interval, what we're doing is we're picking one point in time, and we're finding a upper and lower number, so that we're 95% or 90%, whatever you want, usually 95% confident that the survival function at that point in time lies between those two numbers. So here, that's what I'm saying here, is that the chance that at this particular time, the true survival function is between this number and this number would be exactly 95%, and that would be my pointwise confidence interval. Now, of course, with survival data, a natural question that sometimes arises is, I don't really care what happened at one point, I want to know about the whole curve. Well, we can't do this at every point in time, because we then have a problem of multiple testing. I don't know if you're familiar with that, but if you do repeated testing on the same data over and over and over again, just because you did it, you're going to find something significant. It's the same idea with confidence bands. You got to make an adjustment for every time point that you looked at. So we find, instead of a pointwise confidence interval, a confidence band, which is an upper and lower survival curve, so that we're 95% confident that our survival function over some time interval lies between the lower curve and the upper curve. So it's a band that's good for the entire curve, not just at one single point in time. This is one of the beauties of survival data, that we can do either the pointwise confidence interval or the confidence band. All right, now when you read papers, if only things were for that simple, we could find a confidence interval or a confidence band for the survival function directly by just taking the estimate that we have plus or minus some number from a table that ensures we have the right confidence coefficient times the standard error. This is sort of what most of you would do naively, okay? Turns out that doesn't work well unless you have very, very large samples. So what people have developed is a method where what we first do is, instead of finding a confidence interval or a confidence band for the survival function, we compute it for the log of the survival function or the square root of the survival function or something where it's going to work better for small sample sizes. And then once we get the confidence interval for that, this g of s of t, we convert it back to s. So it's just a mathematical trick, okay? So we have g of s of t plus or minus some other magic number times some other standard error. The most common g's, when you read papers, it may say that it was a log-log confidence interval or confidence band, or an arcsine square root. So those are available to you. And most statistical packages will have these available, and you get to pick them. It turns out that people have shown that you need to make the sort of naive thing I talked about first, of the survival function plus or minus 2 standard errors if you want. You need about 400 observations to make that work, to give you the real 95% coverage. Whereas if you do one of these transformation things, you only need about 30 in each group. So you get much better intervals if you make these transformations. So it's one thing to look for when you're doing these intervals. Okay. All right. So what do these things look like? Here's just a picture for the 3 groups. The thing in gray here is the confidence band, and the 2 dotted lines are pointwise confidence intervals. Now you notice the pointwise confidence intervals are much narrower. That's because they're only good at a single point, whereas the gray is good for the entire curve. So if I wanted to estimate things at 40, I could come up with a confidence interval at 40 as the difference between the dotted values at 40. But I couldn't take the value at 40 and the value at 20 and put those together. I'd have to do a confidence band to get the right coverage probability. And confidence bands are always wider than confidence intervals in doing this. Okay, any questions? Okay, estimate of the mean. Again, the mean is the area underneath the survival curve, so we could take the area underneath the Kaplan-Meier curve, and that should give us an estimate of the mean. Makes sense. The problem is, if you look at the Kaplan-Meier curve, it never dropped down to 0, so the area is infinite. Didn't drop down to 0 because we had these people that were censored. So what we have to do is we look at the area underneath the Kaplan-Meier curve up to some point in time, and we get sort of the restricted mean, or the mean restricted to having the event occur prior to time t. And here's another place where one needs to be careful if you're working on reading this literature, or if you're working with some computer program, you need to know what it's using for the value for the restriction, because that can give you very different estimates of the mean. Common values of tau here are the largest death time or the largest on-study time. And as you can see here, if in our example for the non-myeloablative group we used 53, the mean restricted to 53, that was the last death time, comes out to be 22 something, 22.7. And if we used the largest on-study time, which in this case is 85, then we get a mean of 29.98. So there's ambiguity in using the mean, and most statisticians will not use the mean unless the clinician has twisted their arm to almost breaking because of this reason. Okay, so you need to be a little skeptical if you see it in a paper. Okay. All right, competing risks are in a way easier to deal with and in a way a little bit harder to deal with. Again, remember competing risks, we have multiple causes of death. As soon as one of them occurs, that's the ball game, and we don't see anything else. So what we estimate here to summarize the experience is the cumulative incidence function. The cumulative incidence function, again, is given by this, this formula, which is easy to compute, but again, a lot of computer packages have it for you. And I'll give you a reference where you can get a look at this. And what is this animal? It's just the probability that we've had a type K event prior to time t. If nobody was lost to follow-up, then this is just a count. It's the total number of type 1 events that have occurred up to time t divided by n. So it's the obvious thing that you would have if you wanted to know what's the relapse frequency. You count how many relapses you got, and you divide by the total you had. The problem is with censored observations, we don't know how to count those that were lost without the event occurring. And here's what these animals look like for the transplant example. You can see, well, here we're looking at the cumulative incidence of transplant-related mortality. And the colors are the same as before. And before we saw that those in the blue did the worst. And here they're also doing the worst. Now things are reversed because we're looking at the probability of the event happening, whereas with the survival function we were looking at the probability of it not occurring. But here we have the highest relapse-free mortality, if you will, in the blue group as compared to the other two groups. I hope, since I don't have my glasses on here. Whereas if we look at relapse and look at the competing risk of relapse, we get a slightly different picture. Again, just to refresh your memory what it looked like for treatment-related mortality. In fact, there we had these two groups were kind of right on top of each other. And in reality, there wasn't a whole lot of difference between these groups. Whereas, here we can see distinctly that there are three different patterns of relapse, and that different strengths of the preparative regime, surprisingly, are affecting the chance that a person will relapse more than the death rates. And that's kind of looking at the myeloablative effect of these different results. So cumulative incidence functions as a summary statistic are easy to compute, and they give you information about both causes. As I said, if there's no censoring, the cumulative incidence function is the fraction of cases which experience a particular event prior to time t. Now, if you let t be very large, you end up with something that doesn't necessarily go to 1, okay, because not everybody is going to experience the competing risk. So for very large t, the cumulative incidence function is the probability of having a type k failure occurring at any point in time. And that may well be less than 1. For example, with relapse and death in remission, for very large t, the relapse cumulative incidence is the chance somebody would relapse before they die, and the other one would be the chance that they would die before they relapse, and those two would add up to 1, but they don't each become 1. Okay, the cumulative incidence functions, if you add them all up, you get 1 minus the chance that something happened. S of t here is the chance that you had some kind of a failure, whatever it may be. So adding the cumulative incidence functions up at time t is the chance something happened. Now, as I said, when there is no censoring, the cumulative incidence function is the fraction of cases which experience the kth event type prior to time t. If you look at some old papers, and hopefully it's old papers, in the medical literature, people used to use the Kaplan-Meier estimator, where you could treat occurrences of the other causes than the one you were interested in as censored observations, and then they would plot 1 minus that Kaplan-Meier estimator. And it turns out that that's not correct. It's overestimating the event probability, for one thing. And the second thing is that the cumulative incidence function is estimating the probability of an event, of relapse, for example, in the real world where people can both die and relapse, whereas 1 minus the Kaplan-Meier estimator is estimating in some hypothetical world that doesn't exist, where the other competing risks are not allowed to occur. So if you can find a person who's immortal and ask the question how likely it is you're going to relapse, that would be what 1 minus the Kaplan-Meier estimator would be telling you. And most of us don't have people like that. So for that reason, if you see papers that have 1 minus the Kaplan-Meier estimator, then we don't usually, it's not a good thing to use. Okay. Any questions? Okay, so the last topic I want to just run through a little bit is the Logrank test. And this is sort of the classical test that's used to compare the hazard rates of 2 or more groups. And of course, if it is comparing hazard rates, that's equivalent to comparing survival functions, because there's a 1-to-1 relationship between the two of them. You can use it with survival data. You can use it with competing risk data. It doesn't really matter. And you can use it with some weights to let you look at different parts of the survival curve and see whether they're the same or not. So here's the idea. We have K treatments, and suppose we're at a death time, and we would then know the number of deaths that are in group J and the number that were at risk in group J. Those are these values with the subscript. And then we know the total number that died and the total number that were at risk. Now, if the hazard rates were all the same, then if I wanted to estimate the probability that a person was alive at that point in time, given that they were alive just before that, that's the hazard rate, or you can think of it as a survival function, however you want to do it. That could be estimated by D over Y, where D is the total number of deaths and Y is the number that could have died. Okay? So this is sort of like under the null hypothesis, the chance a person would die. We saw we had a total of Yj people, and the chance that we would have Dj deaths out of these Yj's would be the total number of people that we had at this point in time multiplied by the probability of having a death. Okay, it's just the usual binomial calculation. So this is like the expected value. And then we have the observed value, which is the DJ here. So at a death time, we can look at the observed number of deaths in group J, DJ, minus the expected number of deaths, which is this guy. And if these two numbers are quite different from each other, then that tells us that something's wrong. And what's wrong is our null hypothesis that the groups all had the same hazard rate, or all had the same survival function. All right, now this was just done at one point in time. What we do is we usually take some kind of a weight function, and we weight this difference by this weight function. And this allows us to put different weights on different parts of the curve. If we're more interested in seeing if there's a difference for large values of t, we would have w of t to be large for large values. If we're more interested in what happened right after we started, we would have a curve that was larger there. We take that weight function, we multiply it by the observed minus the expected at each death time, and we add these guys up. And that gives us a statistic Zj that's like a t-test statistic, sort of, like the numerator of a t-test statistic. And then we could do this for each one of the groups, and we can then base our test on all these different groups, Z statistics that we've gotten. Now, the kind of weights that you may see, the standard weight is to take a weight of 1, which is basically no weight. Everybody gets the same weight. We can use a weight of y, where here we're just weighting that we're giving the most weight to differences that occur when there's the most data available to us to make the comparison. So this starts out with a big weight and then gets smaller and smaller over time. Some people think that's too big, so they use the square root of the total number. That's called Tyrone's weight. If you want, you can put a weight that gives weight to any part of the survival curve by using the pooled survival function and using this little formula. S of t to the p, 1 minus s of t to the q, and you can vary p and q. If you had, for example, p equals 0 and q equals 1, then most of the weight is going on time points that were very small. If you had q equals 0 and p equals 1, then since s of t starts at 1, you'd have most of the weights in the other direction. I think I have that backwards. But you can see how by putting it in different points, you get different values. So here's our curves again that we want to compare. And in the example, here's what we get for these tests. Now, what are we doing here? We're testing whether any one of the three groups is different from any one of the other groups. And the p-values that we get for that test are in the last column. And we see here that if we use the Logrank test, which puts equal weight, that it suggests there's a difference between the three groups. If we use the Wilcoxon test, which puts more weight on early differences, it suggests that there's not a difference. Now again, it's putting more weight on values up in here than it is out in here, so it's not unreasonable that it says there's no difference. The Turon and Ware gives roughly the same thing, and the Fleming and Harrington puts most of the weight kind of in the middle. Now, you got to decide on the weights before you look at the data, because otherwise you can always make things significant. It's not fair to decide what the answer is and then find a weight. Okay, I think this is the final slide here. We can take these and we can do pairwise comparisons, and again, the simplest way to do pairwise comparisons is to do some kind of Bonferroni correction to the p-values. So what we have is we have the p-values of the pairwise comparisons here. And again, because of the fact we've done multiple testing on the same set of data, we have to make a correction. And the correction is to take these values and multiply them by the total number of treatments times the total number of treatments minus 1 divided by 2, in this case 3, and we get these revised p-values. And you can see that even though the chi-squared statistic was significant, the pairwise, none of them are really significant. So I guess that's about all I want to say. I have a paper with a couple of the people in the transplant registry that talks about how to analyze unadjusted data in the journal Bone Marrow Transplantation. That's again written primarily for, well, it's written for non-statisticians and clinicians. If you're a little bit adventurous, although maybe with the disclaimer I'm not allowed to say this, you can buy my book that gives you all the formulas and shows you how to do a lot more of this stuff in detail. And as always, this talk was sponsored by the CTSI and Biostatistics, and certainly welcome to come over either to one of our drop-in services. If you have more questions, you're welcome to come over and see me or give me a call and set up something. I'd be happy to talk to you. We have a lot of people in our division who do survival analysis. That's what we're well known for. But you have people here and over at the medical college and Freighter and so on. So, any questions? Okay, well, thanks.